Chapter 6, Standpipe and Hose Systems. Our objectives: list and describe the different types of standpipes and the different standpipe classifications. List and describe the different standpipe system components. State when and where standpipes and hose systems are required in buildings. Reference the design and installation standards that apply to standpipes. And state the minimum standpipe system design pressure and flow requirements. Reference the inspection, testing, and maintenance requirements. Recognize the possible impairments to a standpipe system. A standpipe system is important because it may be the only available fire protection equipment for a structure. Standpipe systems enable firefighters, fire brigades, or occupants to rapidly engage a fire. Standpipe systems are essential when firefighting in tall buildings. Floor levels may be deployed beyond the reach of ladders or aerial platforms. A standpipe system is essentially a network of piping and components that transport water throughout a structure to provide ready access to a water delivery system for manual firefighting. Fixed pipes in the system are between 4 to 6 inches in diameter. The pipes rise vertically or horizontally to feed, hose, valve outlets, or hose stations. Fire protection design strategies combine standpipes and automatic sprinkler systems. The strategies apply to retrofitting an old system or installing a new sprinkler system. The standpipe doubles as a water supply riser for the sprinkler system. Automatic sprinkler systems are usually very reliable, but in cases where manual intervention is required, the standpipe system provides the support. The 5 different types of systems are defined by their operational and configuration features. Operational features refer to the availability of the water supply in terms of immediately available for firefighting, available after the automatic or manual activation permits water to enter the pipe, and the availability only after water is manually supplied through the different connections. Configuration features refer to whether or not standpipe systems ordinarily has water in the pipe. In addition to the 5 types of systems, automatic wet, automatic dry, semi-automatic, manual wet, and manual dry, there is an additional system called the combined system. The automatic wet standpipe. This system contains water in the pipe at all times. It is required to supply sufficient water to support manual firefighting. A fire pump or other pressure maintenance pump may connect to the system to ensure appropriate pressure and flow to operate fire hose nozzles. Once a hose valve opens, the water supply is immediately available, making this system the preferred type. Wet standpipe systems can only be installed when the temperature remains above 40 degrees at all times, such as internal stair towers in mid and high-rise buildings. Automatic dry standpipes. This system contains pressurized air in the pipe. Water does not enter the piping unless a hose valve opens and the air pressure drops to a certain level. The loss of the air pressure allows the system components, such as a dry pipe valve, to open and permit the water to flow through. The water supply must be sufficient to support the manual firefighting. Installation requirements require the water supply of a dry pipe or deluge valve and other system components to be in an environment that is at 40 degrees or above at all times. System piping and hose valves may be stored at lower temperatures. This system might be found in residential, multifamily, or mid-rise buildings. Semi-automatic standpipes. This system contains pressurized air or atmospheric air in the pipe. The pressurized air is used for supervisory purposes and is not related to admitting water into the pipe. Water enters the pipe through activation of a remote control device. Typically, a manual release is located at each hose valve. The manual release activates another device, such as a deluge valve, which allows the water to flow into the pipe. The water supply must be able to deliver sufficient quantities of water to support the manual firefighting operations. Installation requires that the incoming water supply, deluge valve, and other system components be in an environment that is 40 degrees or above. System piping and hose valves may be stored, however, at lower temperatures. This system is common in industrial complexes or public areas where the building features are exposed to varying weather conditions. Manual wet standpipe. This system contains water in the pipes at all times, but it is supplied from the building's domestic water system instead of a dedicated fire service line. Usually, the pressure and amount of available water from the domestic systems are inadequate to support manual firefighting operations. The required water flow and pressure will be supplied through the fire department connection. The domestic supply line tap size is usually not more than 3/4 or 1 inch in diameter. The water in this system serves as a priming water to reduce the time needed for water to reach the hose valve. The system helps detect leaks and reduce corrosive effects on the internal surfaces of the standpipe. This system is still found in older, mid, and high-rise buildings. It is rarely newly installed in buildings after the arrival of the combined standpipe system and fire pumps. Manual dry standpipe. This system does not have an attached water supply. The only thing in the pipe is atmospheric air. Firefighters must connect a water source to the fire department connection to use the standpipe. This system is common in remote or freestanding structures, such as parking garages, where environment concerns and tampering are hard to monitor. Combined standpipe and sprinkler systems. When installing a standpipe and an automatic sprinkler system in a building, the design will try to use the standpipe system as the sprinkler system supply pipe, known as a combined system. This is a common practice in old buildings with existing standpipes, or new buildings where the standpipe design provides outlets for sprinkler systems. Benefits for contractors and developers is it's a manageable design, it's a better use of space, and has a potential cost savings. Benefits for the fire department are it's readily access to an automatic sprinkler system, floor control valve, and manual hose valves in a fire-resistant environment. In 1971, NFPA formally adopted the combined system to promote installation of automatic fire sprinkler systems in high-rise buildings. The requirements included sufficient water supply to support the standpipe and sprinkler system's demand. Had to have a minimum 6-inch supply pipe. The sprinkler system with separate control valves on each floor. Risers, hose valves, and sprinkler system control valves located in a fire-resistant stair enclosure. The only change to the requirements is that if hydraulic calculations proves that the pressure and flow met the requirements, then the supply piping is allowed to be 4 inches. The classification system dates back to NFPA 14, Standard for Installation of Standpipes and Hose Systems. The classes of services in the standards remain the basis for the design, installation, use, water supply, and size requirements. According to NFPA 14, standpipes can be classified into three general categories: Class 1, Class 2, and Class 3 systems. Your Class 1 standpipe systems. These systems are designed for use by firefighters or brigade personnel who are trained to handle heavy fire streams. These systems are common in the following structures: high-rise buildings, open parking garages, covered malls, and underground buildings. These systems must deliver sufficient water at high pressures to support manual firefighting. More than one person may be needed to handle the hose line during suppression activities. Hose connections are required to be at minimum 2.5-inch threaded connections. The hose values are commonly fitted with 2.5 to 1.5-inch reduced caps to facilitate the use of small diameter hoses found in the standpipe packs. Class 2 standpipe systems. This system is equipped to give occupants, fire brigade members, or firefighters access to a water supply through a pre-connected hose systems. Pressure and volume requirements are much lower than the Class 1 or Class 3. This allows easier control of the hose and nozzle so that an individual can start suppression during the initial fire stage. Although occupants have access to water and a hose, the fire department encourages occupants to evacuate. Firefighting without proper training, equipment, and protective gear is extremely dangerous. Many fire departments do not use these systems unless absolutely necessary. There is no way to tell how well they have been maintained, inspected, and tested, so they may be unreliable. The amount of water is not sufficient to control a fire after it develops beyond the incipient stage. The hose stations are often located in open areas that offer little protection to firefighting when preparing equipment to fight a fire. Careful consideration must be given when deciding if a Class 2 system is appropriate. Your Class 3 standpipe system. These systems incorporated Class 1 and 2 requirements to provide equipment that can be used by fire department personnel, fire brigades, and trained building occupants. They should provide a 2.5 and 1.5-inch hose outlets or 2.5 hose outlets with an 1.5-inch adapter. Each hose station allows an 1.5-inch or 1-inch hose and nozzle. Water and pressure requirements are the same as a Class 1, but because of similar safety considerations to Class 2, careful consideration must be given to installation. Many authorities require or suggest a Class 1 system instead of a 2 or a 3. Each standpipe system has a number of required components. Each component has a pressure rating, so when installed, it is able to withstand the pressure demands placed on the system. Factors such as the type and classification system determine the required components. Fire department personnel should be familiar with the components and functions of each. Fire department connections. When responding to a fire in a building that has a standpipe or a sprinkler system, the first responders will connect hoses and lines to the fire department connections, known as the FDC. The FDC is a coupling device found on the building's exterior. The device is attached to a pipe which is connected to the standpipe system, fire sprinkler system, or both. The purpose of the FDC is to provide a primary or secondary water source to the fire department system. Examples: in an open parking garage equipped with a manual dry standpipe system, the primary and only water supply would be through the hose connecting a fire apparatus vehicle to the FDC. Another example: in a building equipped with a wet standpipe sprinkler system, the hose stream might reduce the sprinkler system's effectiveness, making a secondary system necessary to keep up pressure and flow. No control valve can be installed between the FDC and the standpipe system. However, a check valve is required. The check valve prevents water from leaving the system. All check valves must have an automatic drip valve to remove condensation or reduce and prevent freezing or other damage to the pipes. Protective caps or plugs protect the FDC from being clogged with debris. As seen here, the wall-mounted FDC breaches exterior building walls. Freestanding. The FDC supply pipe is buried underground. Once the pipe reaches the right location, it turns up and extends out of the ground to where the FDC coupling attaches to the piping. Most FDCs are single inlet or double inlet threaded. They may be additional inlets depending on the system demands. When the threaded pipe is installed, the coupling must be compatible with the fire department thread standard. Usually the 2.5-inch standard recommended by NFPA 14 is used. When the FDC has more than one inlet, a clapper swings between the couplings. This prevents water from flowing out of one side and allows the hose to be connected and disconnected without the loss of water or back pressure. If both inlets are being pumped into, the coupling finds a midpoint so water can enter through both. The quick connect coupling uses locks or cams coupled with the hose. The couplings align and lock together after twisting 1/4 turn. This type is becoming more common. It is usually used with large diameter hoses, but can also be installed on hydrants. Location of FDCs. The FDCs must be visible, recognizable, and accessible without obstruction. They must meet NFPA 14 requirements. The FDC must be no less than 18 inches and no more than 48 inches above the level of the adjoining ground, sidewalk, or graded surface. FDCs must be within 100 feet of a hydrant to reduce the amount of hose and the time required to connect to it. Other requirements. Many jurisdictions require more than one FDC on buildings over 5 stories. High-rises must have 2 or more remotely located connections per zone. Multiple FDCs ensure continued access for the fire department in the event of damage, blockage, etc. Wall-mounted FDCs are preferred over freestanding FDCs. They have less exposure to the environment. Freestanding FDCs generally receive less maintenance. Freestanding FDCs may be necessary depending on the topography, required hydrant distance, and other safety concerns. FDC identification. FDCs must have identification signs so firefighters know what kind of system they supply. Some FDC supplies only the standpipes. Others supply both the standpipe and the sprinkler system. NFPA requires signs with at least 1-inch raised letters casted on a plate or a fitting. FDC signs must also give information about inlet pressure requirements for the system. This information helps avoid unnecessary delays due to incorrect assumptions. Pipes and fittings. Components used to install Standpipe systems must meet or exceed certain adopted standards published by these associations, such as American Waterworks Association, the American Society for Testing and Material, the American Welding Society, and the American National Standards Institute. Common materials are chosen with consideration given to the pipe schedule, type, and joining methods, and include such things as ductile iron, cast iron, malleable iron, steel, and copper. Fittings join piping and components together by various methods, such as thread, groove, flange, weld, solder, and brazed. Regardless of material, the purpose is to connect pipe and other system components. All pipe fitting and components must be rated for the maximum anticipated system pressure. Gauges. Pressure gauges are an important and required part of the standpipe system. They must be installed at the top of each standpipe. They are recommended on each side of the pressure regulating devices. They should not be exposed to freezing temperatures. Each gauge should have a shut-off control valve and provides for drainage. Gauges can help firefighters and building maintenance determine the available water pressure within the system. Abnormal readings help determine when the system has a problem. Valves. Standpipe systems use different types of valves, including some of the following. Check valves, which are installed between the FTC and the standpipe system piping. Control valves, which allow water to flow throughout the system when open and can isolate parts for service when closed. Drain valves, which permit the water to be purged from the system for testing or service. Hose valves. They allow the fire department to connect to the water supply for manual firefighting efforts. These used to be located on the floor landing level, but now they must be installed on the intermediate levels unless otherwise required. Pressure restricting and pressure reducing and pressure control devices and valves. These devices and valves make it possible to design a standpipe system where the boost pressure is high but manageable. Special care is required to ensure proper application, installation, testing, and maintenance. When appropriately installed, they give design professionals more flexibility. When appropriately tested and maintained, they provide a manageable water pressure for manual fire department hose operations. In the past, these devices have sometimes failed to perform, so it is necessary to perform a flow test at the time of acceptance and periodically thereafter. Merely verifying that the device operates is not sufficient. Flow rate and inlet-outlet pressures need to be verified as well. Failure to install the correct device at the right location or elevation will result in too much or too little pressure in flow. Fire companies and inspectors must identify properties with these devices and make sure all testing and maintenance remains current. Training must include valve adjustments and not just operations. Hose cabinets, hoses, hose racks, and nozzles. Hose cabinets are closets. This is a metal enclosure mounted in the wall of a building. It holds fire protection equipment, including hoses, nozzles, hose valves, and fire extinguishers. It must be sized to house the pre-connected hose and other equipment to ensure easy use during a fire. There must be 1 inch of clearance between the valve handle and any part of the cabinet to ensure the valve can be opened and closed. Even though cabinets usually have glass doors, so the equipment is visible and accessible, they should be labeled. If cabinets are locked, they must have a breakable front, and a device that can be used to strike the glass must be accessible. Hoses. On Class 2 In 2 standpipe systems, an 1.5-inch hose must be lined and ready for use. Be no more than 100 feet long and should be collapsible or non-collapsible. If hose is less than 1.5 inches, it must be non-collapsible. Hose racks. If they hold an 1.5-inch hose, they are required. If smaller diameter, the hose mounts on a continuous flow reel. Nozzles. If installed on a Class 2 system, they require listing and must be able to flow at low pressures so that untrained occupants can use them. The adopted model code published by the NFPA and ICC determines when a standpipe system is required. Specific codes for when to install should be referred to NFPA 14 on how to install. NFPA 5000 Building Construction Safety Code is a great reference, as well as NFPA 101 and NFPA 1 and ICC International Building Code. Many factors affect installation requirements, such as building height above or below the level of fire department access, whether a sprinkler system is or is not installed, the use and occupancy of the building, and of course, the occupancy load. Both NFPA and ICC consider the time and effort it takes for firefighters to establish a water supply for suppression efforts, given the factors above. Before researching installation requirements, determine which adopted model code and reference standards the local, state, and or other approving authorities use. Fully research any hazards that are present and present a unique challenge. Read the code in its entirety to identify any special exceptions. For existing conditions, determine if there were any retroactive code requirements in effect at the time of construction and reference them. Know when a building was constructed, and the code requirements at that time is critical to evaluating an existing system. Requirements based on building height and levels. A building height above ground and distance below grade impact a fire department's ability to operate during a fire. The number of feet or levels above or below fire department access or grade level is therefore the first consideration installing a standpipe system. NFPA 1 requires standpipe installation under any of the following conditions. 1. A building without an automatic sprinkler system that has more than 2 stories above grade, or a building with a sprinkler system that has more than 3 stories above grade. 2. A building has more than 50 feet above grade and contains intermediate stories or balconies. And 3. A building has more than 1 story or more than 20 feet below grade. NFPA 5000 has similar requirements, but a standpipe must be installed when the building has 4 or more stories above grade. Both NFPA 1 and NFPA 5000 have other occupancy-based requirements and restrictions. The IBC states that a standpipe is required if the vertical travel distance inside any part of the building is more than 30 feet above or below the fire apparatus access level. Occupancy requirements. Factors regarding occupancy, such as occupancy load or lack of other fire protection features, may generate additional requirements. Assembly occupancies often generate additional requirements, as listed in NFPA 1, 101, and 5000 in the IBC. All have additional requirements for this type. NFPA 5000 requires standpipes to be installed in non-sprinkler assembly occupancies containing an area that is more than 150 feet from a fire department access to the building. IBC requires a standpipe to be installed in non-sprinkler assembly buildings with an occupancy greater than 1,000 people. NFPA and IBC both consider a lack of a sprinkler system to be significant. The dimensions and open area of a building's design and assembly-based occupancies can affect standpipe requirements. NFPA 101, NFPA 5000, and the IBC all state that performance stages over 1,000 square feet must have standpipe systems and hose connections. NFPA 1 also has additional requirements for airport terminals that are higher than 2 stories or 100 feet or more in dimensions. Buildings under construction, rehabilitation, or demolition. Construction and demolition sites create access and fuel load problems for fire departments. The presence of construction material complicate these jobs. NFPA 1, NFPA 5000, and the IBC all have specific requirements for standpipe installation and FDCs for these sites. Under certain circumstances, a temporary standpipe may be required. There must be at least one hose connection per floor level and a clearly marked FDC at the street level equipped with plugs and caps to protect the FDC and hose valve. Standpipes must expand with each floor. Temporary standpipes must remain in place for the duration of construction. For rehabilitation work, standpipes must be on all floors below and include the highest floors where the work is occurring. For demolition, the standpipe must remain in service within one floor of demolition work. NFPA 14 is the most widely known and used document that outlines standpipe and hose system design and installation requirements. It was adopted in 1915. It has been revised 28 times due to changes in design, philosophy, equipment, and engineering advances. But the basic principles are essentially unchanged. NFPA 14 is cited by NFPA 1, 101, and 5000, and the IBC as a reference standard for design and installation standards. It establishes the minimum requirements for the following: components, hardware, system types, design, plans, calculations, installations, water supply, and system acceptance. It also discusses the requirements for buildings under construction. It clarifies the material used. When designing a system based on the IBC model code, additional requirements do exist, such as the location of the standpipe hose connections, protection of risers and laterals, interconnection, control valve supervision, and cabinet identification and security, to name a few. FM Global's datasheet 4-4N, Standpipe and Hose System, is also well known. FM is one of the leading fire engineering, research, and risk organizations in the world. It publishes and maintains over 300 data sheets covering fire, construction, hazards, and processes. In certain circumstances, such as when insurance requires it, design professionals will use datasheet 4-4N as the basis for standpipe and hose system design and installation, especially as designated by the insurance carrier. N signifies that FM has adopted an NFPA standard, but FM may have made some changes before publishing it. Minimum and maximum pressure requirements. Minimum NFPA establishes the minimum design pressure for standpipes at 100 psi. At the hydraulics most remote 2.5-inch hose valve outlet and 65 psi for the most remote 1.5-inch hose valve outlet. This valve is directly tied to the required pressures for operation of hose nozzles. Lower pressures can adversely affect nozzle operations and water delivery, especially for systems installed before the mid-1990s. Standard operating procedures for many fire departments is to establish a connection between the fire apparatus and the standpipe before beginning suppression activities, ensuring adequate pressure is available. Maximum. Many factors are at play, including the individual's ability to handle a hose under high pressure, pressure rating of the standpipe components, the sprinkler system components in a combination system. Typically, fire department hoses are periodically tested at 250 psi. Trained personnel may have trouble handling a hose at pressures higher than 175 psi. Untrained individuals will have trouble at pressures over 100 psi. The maximum Lister pressure for most components is 175 psi. If the pressure is exceeded, pressure control devices must be installed. Pressure requirements in high-rise buildings. Pressure and flow must overcome pressure loss due to elevation changes, making design systems in these buildings a challenge to create. To get pressures to the top, and pressures on the lower levels must be much greater. Some components are up to 350 psi. Design professionals install pressure control, pressure regulating, or pressure restriction devices to overcome safety and reliability issues that result from such high pressures. Devices may be set up at a factory or in the field, but either way, they must be calibrated to avoid putting occupants and for first responders at risk. At certain heights, it is no longer practical to manage such high pressures. Systems are subdivided into upper and lower zones. Water supply for zones may come from numerous sources. The need for pressure control is minimized by zoning the systems and using high-pressure fittings and devices, all depending on which floor and settings they're on. Minimums and maximum flow requirements. Minimums, as according to NFPA 14. Class 1 and Class 3 standpipe systems must have a minimum flow rate of 500 gallons per minute from the hydraulically most remote standpipe and another 250 gallons per standpipe riser where the building floor area does not exceed 80,000 square feet per floor. For a building greater than 80,000 square feet per floor, 5,000 gallons per minute is required for the second standpipe and 250 for the third if there is no sprinkler system. Class 2 systems require 100 gallons per minute at the hydraulically most remote hose connections with no additional flow required with more than one hose. Buildings with an NFPA 13 automatic sprinkler system have maximum flow requirements of 1,000 GPM. If there is no sprinkler system, the flow requirements increase to 1,250 GPMs. A horizontal standpipe with 3 or more hose connections is required to have a minimum of 750 GPMs. Regardless of the class of standpipe, the minimum duration of water supply to meet the system demand is 30 minutes. Hydrostatic and air test. Hydrostatic test. One of the first and most important tests performed. After installation, it subjects the system's piping, fitting, valves, and other components to a minimum of 200 psi of pressure for 2 hours. Hydrostatic pressure is measured at the lowest elevation point of the system or zone being tested. At the end of the 2 hours, release of the pressurized water from the piping allows the pressure to drop to 0, which ensures a valid test. Air test. Dry standpipe systems are required to undergo a 24-hour air test. It subjects the system to 40 psi of air pressure for 24 hours with a maximum allowable loss of 1.5 psi. The purpose is to ensure that the system does not leak. If weather prevents hydrostatic testing, the air test can be used as an interim measurement of integrity. Most jurisdictions require both tests to be performed on a dry system. The system will be exposed to both water and air pressure. 200 psi of water and 40 psi of air pressure represent the high end of the system the pressure is going to be exposed and are good indicators of the system's integrity. If a dry system is supplied by water through a dry pipe valve, a dry pipe valve test is also needed. Visual inspections. Visual inspections occur in conjunction with hydrostatic test. The inspections include checking for leaks, verifying that components are installed according to approved plans, and ensuring that piping and components are the ones specified by the designer and are approved by the appropriate authority. Visual inspections occur at floor level and is just as important as the hydrostatic test. Failure to complete a visual inspection could lead to system damage, injury of person, and delay of fire department operations. Flushing. Before connecting the standpipe system to any water service, the supply piping must be flushed. This is going to remove dirt, stones, and other debris that could clog or damage the system or compromise its performance in any way. The inspector observes the underground fire service mains and leads in conduction while they flow water. It is a simple process. It is best if the outlets used to flush are the same size as the pipes being flushed. This ensures that any size item that enters the pipe can exit it. The recommended flow rate is 10 feet a second. The minimum flow rate should not be less than the system water demand rate. The inspector flushes it until the water flow is clear. Flow test. These tests ensure the following: that the system delivers in design level of performance. Required flow and pressures are available. Water is flowed from the hydraulically most remote hose valve outlet. A pitot tube and rise gauge help determine the flow and pressure readings. The test usually occurs on the roof. Hose lines, nozzles, and other flow testing equipment are required. The water should not leave the roof. If it must, the affected areas below the testing area should be protected. If there is no roof access, water flow out of a window or down the stairs through the hose and outside the building. Additional property protection may be necessary. A fire apparatus may be needed to pump into the system through the FTC to verify a manual standpipe design. If pressure reducing or pressure regulating hose valves are used, the system must be verified. Failure to do so could result in a deficient pressure or flow. Firefighter training should include valve adjustments if conditions require this activity. Main drain test. If a system is combined or has an automatic water supply, there will be a main drain available. It is piped to an exterior location or an interior drain. It should be able to safely remove the system water so it is not a hazard. It also allows the inspector to determine if the system has an adequate unobstructed water supply. As the main drain valve is open fully, the system gauges display static and residual pressure readings. These readings can be compared with previous ones to see if the water supply has changed. Operation of components. All standpipe components capable of manual or automatic movement must be tested under actual operating conditions. For the most part, the components only require unscrewing a cap or turning a valve to move water through the system. This ensures the system will operate when needed. Periodic inspections, testing, and maintenance. Even if they have never been operated, all fire protection systems must be ready in case of an emergency. Inspection and testing occurs at defined intervals. When components sit idle, their operational condition is not known. They must be periodically inspected and tested. A simple visual inspection can reveal leaks, corrosion, and damage to critical system components. A water flow test could reveal a closed system or control valve. And hydrostatic testing can determine if components are able to handle the water pressure delivered by the pumper. There are many types of impairments to firefighting, some systems related and some not. Physical barriers can create access problems. Firefighters should tour their first due area. There are many potential problems in a system where it is not well maintained. Freestanding FDCs may blow apart when pressurized. Protective plugs and caps might be missing. FDC threads may be damaged or unusable. Problems are often not discovered until there is a fire. At a minimum, periodic fire protection, system inspections, maintenance, and testing should occur. You should follow the schedule in an NPA 25, Standard for Inspection, Testing, and Maintenance of a Water-Based Fire Protection System. In summary, in many structures, a standpipe and hose system is the only fire protection system required and available to firefighters for manual firefighting. Generally, the height, area, occupancy, and hazards determine when a standpipe is required in a new structure. NFPA 14 is the standpipe design and installation standard referenced by all model code organizations. This standard establishes 3 standpipe systems classifications. Discuss the 5 different types of standpipe systems and provide design, installation, use, outlet size, and water supply requirements. Achieving minimum water supply, pressure, and flow requirements for a standpipe system is critical because pressure and flows below could render some fire departments and standpipe systems equipment unusable. This is especially true when dealing with high-rise buildings where loss of pressure due to elevation creates design and operational challenges. Fire department connections are a very important system component. Engine companies should be sure they are clearly visible and operational when needed. Devices that control pressure are another important standpipe system component, requiring identification, documentation, and monitoring for proper inspection, testing, and maintenance. Finally, witness inspections and testing during the installation and throughout the life of any standpipe system is critical. Failure to inspect, test, and maintain a standpipe system could be extremely dangerous to firefighters, especially when a problem is discovered too late to solve. Okay, if you guys have any questions, you can email me at aroberts@athenstech.edu, or you can give me a call in the office at 706-357-0162. Until next time, you guys have a great day and be safe.